So here we're going to talk about a couple of interesting applications of multivariable linear systems. So for our first example, we're going to talk about one from physics, which is if you have the height at time t of an object that is moving in a vertical line with constant acceleration, such as gravity, for instance, then A is given by the position equation, S, which is this. S equals 1/2 at squared plus v0t plus s0. Here there's a lot of variables, but they mean different things. T is technically the only variable actually. The rest of the letters designate, well, S and T are both. T is our independent variable, S is our dependent variable. Here, S is the height in feet, A is the acceleration in feet per second squared, so it's constant, right? We said that it was a constant acceleration. T is the time in seconds, so that can vary. V0 is the initial velocity. You don't have more than one initial velocity, right? When you start off at the time, your speed doesn't vary. It's whatever speed it is at the start. And similarly, S0 is your initial height, okay? So to kind of see the picture here, what we have is you sort of throw an object up, it reaches some sort of a max height, and then it hits the ground later on, right? And this measurement, this sort of height here, if you're let's say we're here at our point, that would be S, okay? Is how high off are you? This would be H, would be S0, our initial height. And the speed we're going upward would be V0, of how fast are we going upward, okay? Well, we're now going to try working out this, we're going to try working this out when we have the following. We want to know what the values of A, V0, and S0 are when S is equal to 52 at time t equal 1, S is equal to 52 at time t equal 2, and S is equal to 20 at time t equal 3. Here, really what we have is we're just plugging values into the system and creating a system of equations. For the S equal 52, so at time t equal 1, S equals 52, which would be saying that when we plug 1 into there, we get 1/2 A times 1 squared, which squares out and becomes just 1, plus V0 times 1 is V0, plus S0, which is, what? S0, which, yeah, just plus S0, because S0 is just always S0, right? Here, we know that when we plug in 1, we get S equal 52. In a similar way, we know that when we plug in t equal 2, we get 52 again. And when we plug in t equal 3, we get S equals 20. And so we can substitute into these equations again. 1/2, 2 squared, sorry. If we square 2 here, we get 4 times 1/2 is 2A plus 2V0 plus still just S0 equals 52. And then if we double this, we get, then if we plug, 3 in, we would get 9/2, 9/2 A plus 3V0 plus S0 equals 20. And this really created a system of equations. Namely, if we multiply this by 2 and multiply this by 2 as well to get rid of the fractions, we would have the system of equations A plus 2V0 plus 2S0 equals 104. We leave that one alone because there's no fractions. 2V0 plus S0 equals 52. And here we got solving, we would have 9A here plus 2 times 3 is 6 V0 plus 2 S0 equals 40 because we doubled everything. And so we have the system of equations. If you go through, you can do your row operations and everything here because here really A is kind of like X, V0 is like Y, and S0 is like Z. And so going through and doing your row operations, you'll end up with getting negative A equals negative 32, V0 equals 48, and S0 equals 20 when you solve that out. And now try and repeat and actually solve the system that you get so try the last example, except this time you'll have different S and T values. On the count of 3, I'll reveal the solution, so you can always skip to that if you just have no idea. But I want to try to really solve it out. So anyways, 1, 2, 3. So we're now going to work a different equation, different example, I mean. But this is going to be very similar to the last example. In fact, in a sense, this is kind of what we were doing before anyways. In a similar way to a line is defined by 2 points, a quadratic equation we can define using 3 points. So let's go ahead and find the quadratic equation ax squared plus bx plus c, whose graph passes through the points -1, 3, 1, 1, and 2, 6. So what are we really saying there? We're saying that if we plug in -1, we get 3. So 3 is equal to -1 plugged in, so that would be 1. So a times -1 squared, I'll go ahead and just write out, plus -1 times b plus c. That happens. Here, we also have that if we plug in 1, we would get 1 back out. So we have a times 1 squared plus 1 times b plus c. And then finally, if we plug in 2, we get, we will get 6 back out, right? All right, so those being points on there mean they need to satisfy that equation where this is x and that's y, right? If we rewrite those out, what we really have here is a system of equations. Namely, we have a minus b plus c equals 3. We also have, this one will give us a plus b plus c equals 1. And then the last one will give us 4a plus 2b plus c equals 6. So we actually have a system of equations here. If we go through and do row reduction on this, we will end up with a, so a is going to end up equaling 2, b will equal -1, and c will equal 0. That is really the unique quadratic equation that goes through these 3 points is going to be y equals 2x squared minus x. And now it's time for you to try one last example. So go ahead and find the unique quadratic equation, y equals ax squared plus bx plus c. Figure out what a, b, and c are, whose graph passes through the points 0, 0, 3, -3, and 6, 0. On the count of 3, I will reveal the solution. 1, 2, 3. So here we end up with 0. We end up with this when we plug in, which gives us this system of equations. We're going to first swap things around, equations around, to get this system, because then it's an easy way to eliminate. It's easy to eliminate in the second equation using the first equation. We then have this. I can also multiply equation 2 by -1/3 to get this system, and then it's just a matter of back substituting to get my answer. For more practice in solving systems application problems using Gaussian elimination, be sure to see the textbook, pages 498 and 499, and work the suggested exercises. In our next video, we're going to sort of standardize this process and make it a little quicker and easier by just focusing on the numbers. Namely, we're going to talk about matrices.